Oh yeah, you want to make your announcement then. All right, that's better.
Oh, good.
And yeah, let me.
Dog that's been at the shelter for so long just got adopted. I mean, it's insane. No one ever thought you were going to get adopted.
All right, let's get going on the lecture for today. Some housekeeping stuff as usual at the beginning of class. Today we're going to talk about water quality measurement. So we did that in the lab last time. Do you guys feel like you learned from the stuff that you heard from Julie?
Yeah.
Yeah, I thought that was pretty good. She's trying to turn this so I can. Good. Yeah, she's really good. Any follow-up thoughts or questions on what you guys learned on I guess it was last Thursday about lab work? What did you guys think about the solids measurement? Pretty precise, right? Like the instruction says to shake vigorously, and that's all. So you can just kind of do it however. Thomas, you've done some sediment work before, is that right? Have you done any solids?
I did a total dissolved solids test once.
Yeah.
Todd did more.
He was the one that did it, that's right.
TSS.
Have any of you guys had to actually do that lab work? Melissa, you've done the TSS before? A couple of you guys have done it. Was that new stuff, just the different ways that you can introduce bias? Yeah. Yeah, the weight is like kind of it's one of those sneaky ones, right? That you're like, oh, the weight could be wrong. Wow, didn't think about that one. Okay, so today we're going to do some more on measurements and how to get the information from the stream to a concentration or a load, like the number that you're looking for your research. Thursday we're going to do Virginia regulations, kind of a short introduction to how we got to the way that the Virginia regulations are set up. And we're going to talk about the runoff reduction method, which is the method that's used here in Virginia to design stormwater BMPs. After that, Dr. Hodges is going to come in and we're going to do some designing of stormwater BMPs here in class using that method. So that'll be a good tool for you guys to know how to use in the event that you guys go into consulting here in the Commonwealth. We were going to do on Thursday the outfall reconnaissance assignment in class where you guys go out and actually look for illicit discharges and various outfalls. We were going to set up like a little ArcGIS online application so you guys could go out and just take pictures and try to identify if there's dry weather flow. But in order to do that, you have to have 72 hours of no rain before you do that. Otherwise, obviously there's going to be water coming out of the outfalls. So it rained a lot yesterday. I don't know if you guys saw it rained like crazy. So we can't do it on Thursday. But just kind of wanted to let you guys know that in the next couple of classes, we may be calling an audible on when we're going to actually do that, just because you kind of have to, if you have a window to do it, you got to do it. And I want to get you guys out there in the field to do it before the class is over. So the schedule, just be flexible with me. I'll send you guys an email. Just make sure and just don't send my messages into the spam inbox like I know you guys normally do. Just kidding. Okay, did everybody turn your proposal in to Canvas? Good. So what I'm going to do with those, the documents, is I'll download them and kind of look over them. I looked over some of them this morning. They look pretty good. And then I'll distribute them to your peer review groups so that you guys can read the other folks' proposals that are in your groups and give feedback. I would like for you guys to do it as track changes in those Word documents, so it's easier to put everything together in the end, so you don't have comments all over the place. It's not the end of the world if you don't do it that way, but please try to make an effort to do that. Those comments, that feedback is due on the 13th of April, and remember that component of it, before you give it back to the person that submitted it, you're going to hand it in to me so I can look at the comments that you made and filter out anything offensive that you said. Just kidding on that too. Please don't do that. And then so you'll be graded on your peer review, but then also, as I said, some component of the final presentation grade will be, you're sort of in this way responsible for the success of your peer based on how effective your peer review is. Does that make sense to everybody? It's not going to be a huge component because I know the peer review process is not like, it's not going to maybe change it that much. But anyway, just wanted to let you guys know, just to be fair with that. Yes, Lauren.
Are you reading over all of them and giving feedback on all of them too, or so there's
Yeah.
your 2 group members
Plus mine. Yeah. Yeah, I want to give you guys as much feedback on them as possible, so I'll look over them as well. For those of you guys that are in Dr. Diamond's research group, maybe some of this stuff will come from Clay. I don't expect him to read them, but I know he's on a lot of y'all's committees and I'm not, so if there's questions that I need to ask of him, you may get some input from him as well. So it should be helpful. It should be a good kind of guiding step. Yeah, does anybody else have any other questions about that, Thomas?
In general, after the proposal, when does it turn into more like developing the project itself?
The project, yeah.
Like, do you keep editing the proposal for it's very specific, or do you transfer to creating the
Right.
project?
So for the class assignment, basically I'm just getting you to like lop it off at the proposal stage, right? But in reality, if you're writing a proposal, that means you're trying to either, one, convince your committee that it's a good project and that they should give you the green light to go ahead with the research. So when you guys have your formal proposal meeting with your committees, at some point they should say, good, like go with it. Here's some questions about what you've done so far that you need to be thinking about as you finish your research. But overall, the idea is good, your direction's good, your timeline looks pretty good. Run with it, and you'll have probably more meetings along the way. So that's for if you're writing the proposal for your master's thesis or your PhD dissertation. If you're writing it to get funding, then obviously the proposal process, at some point, you have to submit it to the funding agency, and that's when the proposal writing ends and the agency says, yeah, we like it, we'll fund you, and then after they fund you, that's when you move from doing the proposal into the actual like doing of the research. But a lot of times what happens is, and this may happen for a lot of you guys with your research proposals, is that it's like you have to almost go a little bit further into the research. Like in an ideal world, you could just do enough work to get the proposal done, right? And that's it, and no more. But in reality, what usually happens is that you go a little bit further in some ways into the research to make sure that the things that you're proposing are actually possible to do. Sometimes you have to do a little bit of that, and then they give you the green light to do your research, and you've already even done a little bit of that research in the proposal writing phase. Does that make sense? So it's not as clearly like segmented off into like proposal writing, research doing. It's like some of it kind of mixes together. Does that make sense? Is that what you're asking me?
Yeah.
Okay. That's a good question, yeah. Does anybody else have any other questions? No? Oh, Melissa, yeah. Okay. Yeah, that should be fine. Are you guys meeting here in Patton? Where are you guys meeting? Oh, yeah. Yeah, you'll have to hustle out there. Yeah, if you guys need to leave in a couple minutes early, that's fine. Yeah, thanks for letting me know. I guess that's a lot of you guys, right? Okay. All right, well, I'll try to make sure that lecture is not going to take the whole thing. Before we start, Zach, do you want to go ahead and make your announcement now before we forget to do it?
Yeah, I talked to mostly everybody, but Dr. Maymon.
Okay, cool. So let's go ahead and get started for today. We went through these slides really quickly a couple classes ago, and I want to recap them just so you guys kind of have the overall sense of what we're talking about here today. So when you're trying to take a sample of a stream, there's generally two ways to take the measurement. The first is where you actually take a some sort of a sampling container out into the field and actually collect a sample of water. You would then either sample it or characterize it there in the field based on what water quality parameter you're interested in, or you would take it back to the lab and do something like standard method 2540 like we saw in the lab last time. Alternatively, they have these newish devices called water quality sondes. That's what one of them looks like. This is a YSI EXO. YSI has some really fancy technologies for doing these things. So this sensor, this device, this blue-looking thing, you mount it in the bottom of the stream, and it's got different sensors mounted to it. And depending on what you want, you can purchase different sensors and like interchange them. This little thing in the middle is actually a wiper. So that wiper circles around and it cleans off some of the sensor heads because they get fouled with all kinds of stuff in the stream, and that can really affect the measurement. This is a really pretty nice tool. I think this particular one is giving measurements at like a 15-minute time interval. I'm sure you could probably make it do it faster than that. But it's only able to collect certain parameters. Okay, so we're going to talk about which ones it can collect and which ones it can't. Thomas, what is the one that's at the LUAS lab?
The MS5 Oxon.
So Hawk builds that one. Okay. Yeah, there's a couple of different companies, the big companies that are making these things. They're not super cheap, so we'll talk about costs at some point today. There's different parameters that can be measured, and actually I should have flipped these because the discrete one should go on the left from the last graphic, but in any case, there's certain parameters that can be measured continuously using something like a sonde or a real-time flow sensor, and then there's others, of course, as I said, that you have to actually collect a sample to do it, and there's actually a couple that traditionally have been measurements that are taken with a grab sample, with a physical collection of a sample, but now there's sensors that are being developed to measure these things. Okay. So we've talked already about depth and velocity and like all the different technologies that can be used to measure those. You guys remember the ultrasonics and the WIRs and the acoustic Dopplers and all of those different devices. So those things are electronic sensors that you mount in the channel, and they're giving you measurements at some high frequency time interval. So those give you more or less, it's not quite continuous, right? Because continuous would be like every millisecond or something to give you a measurement, but continuous for practical applications, okay? A lot of times these sondes, and actually the acoustic Dopplers a lot of times will also measure water temperature. If you guys remember do you guys remember the pressure transducers, the sensor that's mounted on the bottom and uses hydrostatics to measure depth? So if you guys remember that pressure and temperature of water, like they co-vary, so the pressure is affected by the temperature. So a lot of times those pressure transducers will also measure temperature, so that if the temperature fluctuations are dramatic enough in the channel, it can make those adjustments on the fly. Okay. So temperature is a fairly straightforward one to measure continuously with some sort of a gauge. We also can do oxidation reduction potential, or ORP. Turbidity is just sort of like a light transmittivity measurement. It's the ability for light to pass across two sensor nodes. The units for that are either the NTU, which I think is like nephelometric turbidity units, and FNU is something similar. And that's just like a unit that they've established to say how easily can light cross this water. Okay. Dissolved oxygen, pH, specific conductance, et cetera, et cetera. So this one, I think, this particular sensor is doing, I think, all of these 5. Yeah, and actually this one too, so it's doing 6. The ones with the stars at the bottom, nutrients and carbon, the carbon species, again, I have them starred because traditionally those have been something that you have to take a grab sample of and take them in the lab and actually do the nutrient analysis, as Julie was talking about last time. So let's talk about nutrients first. There's actually like an open competition right now to develop a really accurate and effective real-time nutrient sensor. So as you guys know, here in the Chesapeake Bay, nutrients are a huge thing. Also true out in the Midwest, in the Missouri and the Mississippi River. So the Geological Survey and all of these instrumentation people have gotten together and they said, we really got to have something like this. We really need a real-time nutrient sensor. Somebody needs to develop it. Let's put basically a cash prize out there for someone to do that. So I think that they've developed some that they kind of work okay. Maybe they're not terrific, but there's progress that's being made towards the nutrient sensors, and I think the carbon sensors as well. But they're still not they're not great, I guess. But in any case, if one of you guys knows how to do that, it might be something interesting to pursue as a research project. For PCBs, you guys remember talking about PCBs, the endocrine disruptors and the carcinogenic organics that come from industrial processes. Typically, we would do a discrete sample and characterize them in the lab using one of the EPA methods, but there's this new, it's kind of like a fake fatty tissue that you actually just mount it in the stream and you allow it over time to accumulate these PCBs in that fatty tissue. It's called an SPMD, or semi-permeable membrane device. The idea there is that you have some time frame over which the PCB accumulates in that fatty tissue, and based on that you can kind of estimate a PCB loading from the stream. So that's a newer method. It's pretty tough. The concentrations in the water column of PCBs are pretty low, so you actually have to leave it out for quite a while to get a decent reading. But it's kind of a neat idea. It's sort of almost like a simulated fish, if you can imagine. You can imagine that. Okay, the column over on the right-hand side are the various constituents that we would actually have to do some sort of physical sampling, some sort of physical characterization. You guys remember the biological life methods where you're kicking around in the stream and actually counting the critters. The bacteria would be some sort of you would have to incubate, you'd have to feed and incubate the bacteria over some specified time frame to grow them, and then you would maybe count the number of colonies that form on a little filter or something similar to that. But in any case, you can't really do that in the field, right? There's no, as far as I know, unless someone knows of something that's just recently come out, there's no way to just stick a sensor into the water and have it tell you how many indicator bacteria or indicator organisms are living in here. Does anybody know if there's something like that available? I remember a couple of years ago there was a Gates Foundation grant where he was trying to pay people to try to do that. Okay. So still no one's figured out how to do that. Actually, an interesting side story. One of my undergrad advisors, his name was Joe Brown. Did you ever know Joe Brown, Amy? I don't know if he was at Alabama when you were there. He was the young, mad scientist genius guy. And I got to know him as an undergrad. He was a really cool guy. And then I graduated and went to work in Houston. And he called me randomly one day and said that he actually was the guy that won the Gates Foundation grant for this project to try to develop some sort of a sensor for fecal coliform. I think it was fecal coliform or something like that in drinking water. And so he was the grant was incredible. It was several $1 million. And he was like, hey, I really need grad students. Can you come back to grad school, please? Or tell me people that wanted to go to grad school because I need people to work on this. And I was like, I don't know anything about fecal coliform. I'm sorry. Anyway, it's a little side story there. So if you guys, let's think about some of the important information that you're trying to get at with these measurements, right? You're looking for concentrations, right? So you want to know what is the concentration of one of these many things in the water, and you also are interested in loads, right? So the load would be the concentration is going to be a mass per volume, so a milligram per liter, and the load, it may just be a mass per time, let's say. So if we're looking at an annual load, we're interested in saying, over the course of a single year, how much sediment crosses this particular section of river. Okay, so with these discrete samples, we typically are measuring concentrations, right? Okay, with these, a lot of times we're not even measuring concentrations. Like the NTU, it's not a concentration. It's just a random unit, right? So when we measure this turbidity, typically what we're trying to get at is something like this, total suspended solids or total solids or something like that. So what typically is done is that a relationship curve is developed such that we can measure, let's say, turbidity real time at really short time intervals, and based on grab samples that we've taken that we've related with turbidity measurements, we can develop a rating curve, right? So the idea, this is actually a better kind of way to think about it. And this is not TSS. This is the USGS's TSS. It's suspended sediment concentration, I think is what they call it. And the idea is that it's a function of these different variables, these different water quality parameters. So this particular equation uses turbidity in particular. That's usually a really strong indicator of suspended solids concentration. But you could also use specific conductance. You could also probably use either flow or depth in there to see, what is, if I'm measuring all of these other things real time at high frequencies, and I'm trying to get a concentration out to measure an annual load, this is how you would do this. Okay, so you build like a statistical model basically of all the real time parameters to try to estimate concentrations, and then you compare those to your observed concentrations, which is shown here. It looks like it's a pretty good fit for this particular site. Okay. So again, the idea is that we couldn't possibly take enough grab samples to estimate a load, right? We've got to have some way of comparing the grab samples that we're able to take to those high frequency real time measurements that are getting picked up at higher intervals. Okay. Does that relationship make sense to everybody? The way that let's say turbidity is related to solids and why they do that. You guys understand that? Okay, we'll talk a little bit more about that in just a second. Okay, so there's a couple of important considerations in terms of the field methods, right? In terms of just actually gathering the sample out in the field. Okay, so one of the important things, of course, is maintaining your site. So let's say that one of you guys is interested in a particular reach of Strubles Creek, and you want to install some flow and water quality sensors in that reach. Okay, so probably what you're going to want to do is at the beginning, once you've installed it, you're going to want to go out every week and look at what's happened to your site. Okay, because if you don't, there's just any number of things, right? You could get all kinds of debris hung up on it. The cross section might fall apart during a rainstorm event. Your sensor might get covered with, for example, a large piece of concrete, which is what's happened in that one, or completely covered in sediment. So there's all these different things that could happen. At the very beginning, you want to be out there at least on a weekly basis. As you start to get a feel for how the station is working, you can back that off and spend maybe once every 2 weeks or maybe once a month visiting these places and checking them and cleaning them. What happens is that if you don't do that, you really have no sense of how valid your data is for your research work, right? You get these erroneous measurements, or maybe the measurements look just fine, but they're really not, and you use them and you come to spurious conclusions in your research. Okay? So maintenance is really important. It's also, if you zoom out a second and think about the overall effort and cost required to develop one of these monitoring sites and do one of these sites for your research, it's actually a really considerable effort to do it, because not only is it kind of a tricky thing to pick out the sensors and install them correctly in the channel and develop your rating curves, but now you've got to be spending, depending on where the site is. I mean, if it's in Strubles Creek, you could just walk over there, but let's say your site is out, out in the James River somewhere, and you actually have to drive out there. So now you have to drive out there, clean the sensor, make sure it's working correctly, drive back. So now we're talking about quite a bit of time to actually make one of these things operational. In addition to the maintenance of the sensors, another thing that you have to think about is, can the measurements be compared to some sort of a benchmark? Can we calibrate the measurements over time to try to understand if the measurement that the thing is giving me, if it's actually true to what's happening in the field? So depth is a pretty easy one. I mean, you can go out there, plug your computer up to the sensor, look at what is the sensor, how deep is it saying that the channel is right now, and then basically just measure how deep the channel is, and you can compare that, right? And if you need to adjust it, most times the sensors will have some way of saying you're too high or you're too low, or basically telling the sensor this is how deep the channel is right now. Some of the other water quality constituents are more complicated though. Okay, you have to, either the sensors, the water quality sonde will come with some sort of a standard that you can compare your sensors measurements to the lab standard and try to adjust accordingly. But in any case, this is also a component of trying to make sure that your system is working correctly. Okay? And it's, I think once you get the hang of doing it, you get in a routine, it's really just it's not that difficult, but learning how the calibration works and learning how to adjust the sensor. Sometimes the way that the computer interacts with the sensor, I've used programs before that do that, and it's like, I don't even understand how this works, right? You have to know some command line scripting to make the adjustments, and it's complicated. So that's all to say that it's, when, I realize that not a lot of you guys are probably planning to develop one of these sites for your research, but in the eventuality that you did, you have to know that the effort required to do one of these is pretty considerable. Okay. What else do I want to say here? I think that's it. The bullet point here about sensor failure, just in my own personal experience, I haven't used a whole lot of sondes, but I have used a lot of the acoustic Doppler sensors. And one of the things that we identified that happens a lot of times with those is stuff like this, right? Where you have something completely blocking the velocity sensor. This is also an interesting problem because if you guys remember, that sensor uses the difference in pressure between the water pressure and like an open to atmosphere to estimate how deep it is. And there's a pressure tube in that line. Okay, so inside this line is some electrical communications cable, but there's also a hollow pressure tube that goes through that's open to the atmosphere, right? So what do you guys think would happen in this case to that pressure tube? Yeah, so there's that debris jam that's hung up on the cable. You can see the cable is right here, and the cable is connected to the back of the sensor back here. And so what's happening is it's kinking that pressure tube. So the pressure, the depth is related to the pressure, and if that pressure tube is kinked, then of course the depth measurement's not going to be right either, right? So these things, what we had to figure out how to tuck the pressure cable into the joints between the culverts and tack it down in there with these strips to make sure that this doesn't happen, because there's always, it's a storm sewer system, right? There's always stuff flowing through it. But one of the worst things is plastic bags. Plastic bags always seem to end up on those cables, and then once the bag gets hung, then all of these branches get caught on it and they start pulling on the cable. We have one of those things in our office, I think it's still in there, that the cable actually just got ripped out of the back of it. So great, $3,000, right? So I think that's the last thing I want to say about this, but surely there's lots of issues regarding measuring these environmental variables. Let's talk about laboratory analysis. You guys got to see some of this in action last time. Julie talked about standard methods. This is what the newest edition, I think this is the newest edition, looks like. We have that available in Durham. Jody, the lady who was working on that thing that was on fire, She is the one to ask if you need one of those. The Standard Methods book, it's been around for a long time. It's gone through various iterations of review and improvement as the methods get better. They keep updating it. So I think Julie mentioned that a lot of the methods used to use mercury, and so they're trying to kind of get those out of the standard methods as time goes on because of how nasty mercury is for us. In the literature, you'll see this referred to a lot. We use standard method whatever to characterize, let's say, nitrogen or phosphorus or whatever species. And it's one of those things that you don't really have to explain it. You just say we use this method, and it's good. Like that's all you got to say. So for your own research, it's okay to do that. But then also as you read papers, you'll probably see that stuff mentioned. Some folks will also say that they use EPA methods, which are similar to standard methods. They're standard methods. You actually have to buy the book. You have to have a copy of it, but the EPA methods are available online. This website, the NEMI, if you go there, you can look up any of the EPA methods, and you'll get a PDF document for them describing how it actually in the laboratory. How do you do this procedure? And it will give you stuff like precision and bias issues, known interferences, like what we were talking about last time. It's good stuff. If you guys are doing a lot of work on any sort of particular species, even if you're not doing the lab work, it's really good to actually go and read these things to see how do you actually get a measurement, right? How do you get a concentration out of this water quality sample, okay? I think that's all I want to say about those. I don't want to really describe any of them in detail. This next slide is focused on the solids measurements. So last time we looked at this particular one, the standard method 2540D, and as you guys remember, there was various ways to introduce error into that measurement. There's actually been quite a bit of research into how erroneous those measurements can be. This particular graphic is from a paper by Clark and Sue that I thought was pretty helpful. They compared the three different sediment methods that are really commonly used. So we've got the EPA method, the standard method, and then the new one. And as I said, this is the one that the USGS uses, the SSD. It's an ASTM method. Kind of interesting to compare the different specifications for how to actually do it. In terms, it's really the same. You've got your sample, and you're trying to get the solids out of that sample in some way and kind of measure the amount of solids in that sample. So you can think about it generally in the same way, but the way that you technically do that is different between those three methods. Okay? So this is kind of interesting, right? The filter pore size in the EPA method, it doesn't even actually say what filter size you use. So if you use the EPA method, you have to report that. And actually, the standard method is the same thing. It has to be less than 2 microns, but if it can be anything smaller than that, right? You just have to report it. So that this one tried to kind of clear that up a little bit. You guys remember seeing the stir plate, which is of course really cool. The EPA method, they just say to shake it, right? To shake the thing vigorously, which is like, well, how vigorous is vigorously? And let's see. The ASTM method, I love the word supernatant. I use that word all the time. I don't even know if that's how you say it. So let's see. You actually flush. With the ASTM method, the difference is that you use the whole sample, basically. You take your sample bottle out of the stream, and instead of pulling an aliquot out of that sample, you use the whole thing to make your concentration happen. And to do that, you've got to rinse the whole thing with DI water. And so it's supposedly a little bit more robust to some of the particle size distribution variants that you'll see in stormwater flows, but the standard method is pretty well accepted. So just kind of showing you guys the distinction between the things. Okay, as I said earlier, there's two important pieces of information typically that we're trying to get as stormwater people out of the measurements, the field sampling and the lab characterization. The first is the concentration, and the second is the mass load. Okay, so the concentration, the reason why we are interested in it is because a lot of a lot of EPA thresholds and water quality standards are based on those concentrations. Okay, so if you think about what the concentration actually means, it's sort of like it's a mass per volume. So we're looking at a given sort of control volume of water, and we're saying for that volume, how much mass is in it, and then maybe for the EPA standards, you could say how much is safe in different ways, right? There's acute and chronic toxicity standards and thresholds. So that, I think, probably makes pretty good sense to you guys. Okay, it's straightforward, right? What is a concentration? Now, this one is a little bit more. There's a little bit more information required. So to calculate mass loading, what we're thinking about is instead of a mass per volume, now we're thinking about it as a mass per time, or sometimes just as a mass. Okay. So if I say what is the annual mass load of sediment in Strubles Creek, that would just be a mass, right? It wouldn't be a mass flux. But if you're doing a mass flux calculation, this is how you do it, right? You're taking a discharge measurement and you're taking a concentration measurement, right? So discharge, what units is discharge typically in? Yeah, so we've got, but if you break that down, what is cubic feet? That's a volume, right? So with discharge, we got a volume per time, right? And we're multiplying that volume per time by a what? Mass per volume, right? Concentration's mass per volume. So the volumes cancel out, we get a mass per time. Does that make sense to everybody? The units are goofy. We've got CFS, we think about CFS in milligrams per liter, so you have to do a unit conversion to make that work. But this is an important calculation. Okay? It's really important because TMDLs are typically based on these, on mass fluxes. Okay? They're based on how much mass is currently flowing through the system, how much mass is okay to flow through the system, therefore how much do we have to reduce that mass load. Okay? So important calculation there. You can also normalize this, so that's what this bullet point is saying. You can also normalize that by an area. You can say, okay, on an area basis, what is the mass loading per year? And sometimes that's a helpful way to compare two areas of different size to each other. So if you have two watersheds, you can look at they call it the unit area loading, or UAL. So it's sort of like on a unit area basis, what is the loading from this area? So I can compare one watershed, let's say, to another. Okay. Does that make sense to everybody? Yes, Zach.
In order to do a mass load for like a year, do you have to have data for the whole year, or can you just have it for part of the year and extrapolate it out? Because it seems difficult to have.
That's a really good question. That's a good question. So the the I's in this equation mean individual measurements. So if you think about that, the I could be, I went out in January and February, I went out once a month and took a flow and concentration measurement. And then over the course of the year, I did that summation, right? So every time I do that flow and concentration measurement, I estimate a mass flux, and then over the course of the year, sum all those up, and that's my annual loading. But the I could be, as small as minutes, right? But the idea is that you got to have both. So you could probably, depending on what your study is, you could probably get away with monthly estimates. But again, that's based on what you're trying to do with your study. For a storm event, you're going to really want flow and concentration over the entire hydrograph. So in that case, we're talking about flow and concentration measurements on the minute basis, right? So actually, let's do some calculations now. And what I'm going to do is I'm going to change the terms of this equation for this, because this kind of works out. You can use flow or volume, but we're going to use volume for this because it's a little bit easier to understand. Okay, so this sort of measurement, this metric, the event mean concentration, is sort of like the average, kind of the average concentration over an entire storm event. So if you guys would get on Canvas, I have an Excel spreadsheet that's posted up there that is showing, it's an in-class example problem on how to make this work. It looks like this. Let's see. Maybe I can. Okay, you guys give me a nod or something when you're there. You guys got it up? Good. Okay, so I think in the example I've got time, discharge, and TSS concentration up there. Is that right? Okay. And then I think I've got the column set up. So volume, and then VICI. So that's the question that Zach was asking about. So the first step here that you're going to want to do is do an estimate for volume, right? You're going to want to calculate using your discharge column and your time column how much volume is passing through during each time step, okay? So if you guys would do that, let's see. It's going to be hard to do this like this. Four times, let's see, we got minutes. Am I multiplying that by 60? Is that right? Or dividing by 60? Cubic feet per second. Times 60 seconds per minute. I think it's times 60. Yeah. Okay, and then those numbers look all right to y'all? Oh, that's supposed to be in liters. All right, so we got to convert that to liters. So right now I'm in cubic feet. Okay, so there's 28.3 liters in 1 cubic foot. So then I think I'm just going to multiply this by 28.31. Let's say, or 32. And then let's bring it down. Am I dividing by 28? Does it multiply? I had cubic feet and I wanted meters. Okay, so I'm getting in the hundreds of thousands of liters. Are you guys? If you're having trouble doing it, it might be because I made the text white at some point. So just make sure that your font is black in those cells. So the first idea here is something that we've already done. We're just calculating runoff volume, right? We're not doing direct runoff. We're not separating base flow out or anything like that. We're just saying how much total volume went through over that time interval. And then the next step that we want to take, where is my cursor? Oh, I totally lost it. Here it is. It's going to be this next column, right? So we're wanting to do a mass, okay? And you guys remember, we've got, in order to, is everybody caught up? Are y'all in good shape? Good? Okay. In order to calculate that mass, we've got these two concentration measurements that we've got to kind of, I guess, integrate sort of into this volume. So we're saying concentrations for these two flow rates here, the 20 and 20, are the 0.1 and 0.1. And so what we're going to do is, for this calculation, we're just going to say, yeah, this is so goofy. Let's see. I think we're just going to use the average of those. So let's do equals, let me turn my column so it's black so y'all can see this. Because right now it's not. I'm actually going to do this calculation too. Okay, so we're going to do the average of those two concentrations, so plus that divided by 2, and then we're going to multiply that by our volume, right? So we're doing milligrams per liter times liters to get milligrams, okay? Just drag that one down. And then I've got at the bottom sums, okay? So I've got a total volume that has passed through the, across that cross-section based on the volume calculation. So that's just the sum of the volume column. And then this is just the sum of that mass column. For what? Yeah, so it's just, you're taking these two concentration measurements and averaging them, and then you're multiplying that by the volume in this cell right here. So take these two and multiply by this one, because we're trying to get from milligrams per liter multiplied by liters to get mass as a concentration, or as a milligram. So now we have those two columns filled out. That gives us the two sums at the bottom. And if you guys remember the equation for the EMC, we've got it down here at the bottom. You guys think? You got it, Megan? I have the thing showed, the EMC calculation shown graphically here. Maybe this will help a little bit. So the flow rate is in blue, and that's over here on this side, so you don't really probably need to worry that much about it. But in orange, I've got the hydrograph showing, or I should say the polutograph, showing the TSS concentrations that we took across the hydrograph, right? So you can see measurement, all the way across through here. And what we're doing is we're saying this green line is kind of like the average. It's like the average concentration across that entire polutograph. We're using the entire volume that went across, and we're using all of the concentration measurements that got taken across that rainstorm event, and we're sort of averaging that. We're almost like flow averaging the concentration measurements. Okay. So this is a pretty standard way to do, like if I'm interested in saying like what was the concentration of flow or I should say the concentration of, let's say, solids during a rainstorm event. This would be a pretty easy way of describing that, right? The EMC was 20 milligrams per liter, let's say. Now, if you think about this, you can actually, let's go back to the PowerPoint. I'm going to jump a slide and then I'm going to come back. I'm not going to come back if I don't. So these things, and some of you guys I'm sure have seen them, but these devices, they take the samples for you. So they have a tube that goes out into the stream. They suck water in. The way that those things know how to take a sample is based on a flow measurement in the stream. So the computer system up there is listening to the flow sensor, and the flow sensor says, take a measurement now, take a measurement now, take a measurement now, and that's based on the integrated volume that's passing through that cross section. Okay, so what this graphic is showing, it's the same sort of idea, except that we've got turbidity, we've got green, like the green line is turbidity. The sample itself from this guy is shown in pink, so you can see that thing is drawing samples at different points along the runoff event. And then the stage measurement, which is for the USGS station, it's sort of related to discharge. The stage measurement is also shown there. Okay? And the idea here is that auto sampler, this device, is trying to pull concentration measurements out of the stream at the important points of that rainstorm event. So we've got peak and peak and peak, and actually it's doing a really good job, right? Because it's taking a sample almost exactly at where the peak of the flow is, right? And that's really what we want. We want it to try to say where the important. So let's say you didn't have turbidity or stage, like real time, and all you had was the purple dots, right? If we took away the other real-time information or the high-frequency information, all we would have is the purple dots, which it would look kind of weird, but we would still have some sense of, oh, it peaked, it came back down, it peaked again, it came back down, and we probably cut it off here, right? We try to just connect these dots pretty simplistically, but for, I don't know, 10 measurements that it took, that's pretty good, right? That's a really nice way of sampling storm flow, is you connect your auto sampler to the flow measurement device and get that device to tell you across the flow ranges when do you need to sample. Because if you're out there grab sampling and doing that kind of by hand, it's pretty hard to know, where's the peak, right? Like when do I need to be taking those samples? Okay. Okay. I'm going to go back one slide and then we're going to come back to this. I want to talk about cost for a few minutes because these devices are pretty expensive, and for a full sort of chain of custody, it can get overwhelming. And again, this is why if you're trying to do this as a research project, it's good to kind of think these things through at the front end. But these are some really rough estimates for what it takes to do instrumentation for stormwater flows. You can get simple flow sensors for about $1,000 to $3,000. The SONs are on the order of tens of thousands. They're pretty expensive devices. I think maybe you can get them for a little cheaper than that, but not much. The auto sampler, the device we just looked at that has the system that collects samples on demand, about 10 to 30K. Ultrasonics, you can get them for really cheap. So these little devices, you can get them on the internet. Here's an example of one that's about $35. But the low-end ones, you have to do your own programming and try to figure out how to make them work. Really, what you want to purchase is something that's got the system kind of built already, that you just plug your laptop in and it tells you what the depth measurement is. So those are going to be a little bit more expensive, probably a couple $100. Just for a sort of point of reference, the Geological Survey and the gauges that they install across the U.S., on average, they kind of cost those stations out at $50K for construction and about $50K annually for operations and maintenance. Now, the actual cost varies from gauge to gauge because different gauges are a little bit different, but just for the sake of budgeting and trying to, figure out how to allocate money, that's kind of like a rule of thumb that they use. So is that surprising to you guys that it's that expensive, or is that, I haven't really seen any response from the audience here, but I mean, does that seem like reasonable to you all, or is it like a lot of money? What do you guys think?
I think it's a lot of money for to monitor one stream and one water.
In one
And to think
location,
about
right?
How many that they have and that they do keep up.
Right, right.
Crazy.
Right. If you look at the national network of stream gauges across the U.S., there's a lot of them. So you think about how much effort and money it takes to keep all of those things going. It's a lot. It's considerable effort. Those estimates for the survey, these things right here, they include this stuff: telemetry, the power. Sorry, Amiana, do you have a question? Yeah, you would be surprised at like all the things that happen. Like so the one that we had installed in Roanoke, they had to, I don't have the picture up. So first of all, you got to think about like man hours, right? It takes time to actually construct the stations. It's not actually as easy as like just going out there and like screwing the thing into the channel or installing it somehow. It takes probably like, I'm going to say like a week to 2 weeks of probably 2 guys working on it to get it installed correctly. And you have all this stuff like telemetry, which is like the communication system. You got to get the power going. You got to actually build the housing. So most of these things, like this one right here, this is a GS gauge up in Northern Virginia. They have like a tower that's built around it. It's really just a corrugated metal pipe, but they had to get contractors out there to dig the hole and put the foundation in it. They had to build a little bridge to actually get to it. So it's like man time, plus you've got like these sort of intangible things that, you've got like concrete and wood and just various things that come up. This one in Roanoke, they had to, what happened? So they wanted to run, they had the sensor was in the stream, and then right next to the stream there was it's like a greenway. So there's like a running trail right next to it. And they wanted to install the box, like the housing for all the instrumentation on the other side. So they had to get like a what do they call those things? It's one of those devices that you can bore a tunnel underground without digging, without trenching. You just like, it's like a yeah, it's like a trenchless system, so that it's like this huge like hydraulic ram that like shoves dirt out of the way, and that didn't work. Like they broke the greenway, so then they had to like drive the truck. Do you remember seeing this, Melissa? They had like the truck parked on top of the bump in the greenway to try to like make it go back down. I'm recording this, probably isn't good. I didn't even think about that, but anyway, they like all of these things happen, and it's just not that easy to install it. They had they put a big pipe casing underground to like get all the communications through there, and they had to wire it up, and then they have all these programming. Plus, and I'm totally going off on a tangent, but it's a good question, Amiana. Plus, the infrastructure to get that information from the box to the internet, currently it goes up to this satellite called the GOES satellite, which is like a bunch of federal agencies share time on this thing. But they have this antenna that's just aimed like the perfect angle, and every hour they have, do you remember, Melissa? It's like it's a minute maybe, or something like that. It's some like really small time frame that they're able to send their information. Yeah, but I mean like the time window that they have to actually send the information to the satellite, it's like really small. So they have to like, all the data is like collecting there in the computer, and then it's like, there's like, each one of the stations has this really high quality timer on it, or a clock that says, okay, station go, like send your information, and like sends it up there as quickly as possible, and it shuts it down. But there's like thousands of stations that are having to do that. The satellite picks it up, sends it out to the servers where it's saved, and then it appears on your computer. It's all invisible to us, right? But the sort of like the effort, the manpower to keep all those servers going, to keep the GOES satellite going, it's just like, it ends up being a huge effort. So anyway, I totally went off on a tangent on Amiana, but that's in the background. Also, an interesting side note, and we're supposedly I have a slide for telemetry sets at some point in here, but The survey just got access to this new satellite called the Iridium satellite, which sounds really cool. And the Iridium was like I think it was a Department of Defense's communications satellite, so it was like real time, right? They could get information from all over the world just like as quickly as they needed it. And for whatever reason, this thing just became available to the survey. So now it used to be that there was like probably about an hour time lapse between the measurement taken itself and it appearing on your screen. But now that this Iridium satellite is available to the survey, they're going to start moving everything over to that system. And I think it's going to be like on the order of 5 minutes, which is really cool. So like the information's going to get taken in the stream, and then in 5 minutes, it's available on your screen, which is like, wow, that's crazy. Maybe I'm the only one that thinks that, but okay. So I went backwards, right? Now I need to go forward too. We talked about this with Julie last time. Between the time that the sample is actually taken in the stream and the time that it makes it to the laboratory, something's got to happen with that thing, right? Like either it's stored in a refrigerator, so like this graphic here is showing the auto sampler is sending the samples into this refrigerated unit that's in the box, the storage box, and then at some point someone's got to go out there and actually get the samples and fill out the chain of custody form and drive them over to the laboratory, probably in a refrigerated van or something like that. The storage and preservation actually for not all parameters, but a lot of them is pretty important. You can have microbial degradation happening in your sample if you don't refrigerate them, which can significantly affect the actual measurement itself. So big consideration. We've already talked about lab characterization and, of course, the different methods. This is another graphic from Clark and Sue. So what this is showing is for the USGS's SSC method, we've got standards. So we've got known concentrations here on the x-axis, and we've got the SSC measurement on the y-axis. Pretty nice, right? The one-to-one, like it's hitting that one-to-one line almost perfectly. But when we do the same thing for TSS analysis, using, this is EPA 160.2, so this is not the standard method. But if this is the one-to-one line, right, so this would be perfect measurement. We're falling pretty well below that depending on what the characteristics of the sample are. So sand and silicon dioxide kind of bringing that down below 1-to-1. Okay. So just another note on sampling error. Wanted to show you guys this graphic quickly. We're running out of time here. I'm on 15. Let me see how much I've got left. Make sure I cover all the bases. Yeah, I think I can make it. Talk fast. So all of these different measurement components have some precision and bias uncertainty associated with them. And when you start compounding them, so you've got the flow measurement, you've got the water quality, samples being taken, you've got storage and preservation, you've got the lab characterization itself. So when you start putting all these things together, the uncertainties start to compound, right? So you have this individual component uncertainties along the way, but then at the end, if you're trying to figure out, well, how close is my sort of measurement, my final measurement, to what's actually out in the field? In order to estimate that, you combine them using this equation. We're not going to use that really in class or anything like that, but it's an important one to know because you would just take all of the components of the uncertainties, square them, and then find the square root of that to calculate the combined uncertainty of the sort of the whole thing. Okay, so that's probably, it's going beyond really what we need to do in this class, but it's an important one to know. And what this is showing is just for an example, BMP monitoring study. That particular study used a couple of different methods to measure. I think for this one, I'm looking at. Yeah, I'm looking at phosphorus. So you would just take all of the component uncertainties, which are here on the x-axis, and use this equation to estimate combined uncertainty. Okay. Okay, so that was the focus of that slide was on uncertainty. This one is on power. I talked briefly about this, but it's an important consideration in the field sampling. Trying to make sure that your sensor system has a stable source of of power can end up being kind of a tricky thing. This graphic right here is showing a system that was designed, I think it was designed to be set up on solar power, which I always get them backwards, AC and DC. But in any case, it was designed to be set up on solar power, and we were using it in the lab, so I couldn't use a solar panel, obviously, unless I like mounted it outside. So I decided to get like one of these AC/DC converters to plug it up into the wall and kind of Frankenstein the system to make it work. But if it's underground, you have to do something like that, right? You have to have some sort of a stable power source, either to run power from from Appalachian Power or whoever to keep your system going, or you've got to have solar to keep it going. And it actually ends up being kind of a headache. Data management is also an important one. This is the other side of the telemetry that's like, it's hidden. So like underneath this geological surveys, National Water Information Service, there's these huge databases of time series information from all their stations across the US. For a particular research project, maybe not data management is maybe not as big of a deal, but if you think about a year's worth of 5 or 15-minute data, all of a sudden you've got a huge amount of information on your hands, and an Excel spreadsheet is going to start to break down. Right? You're not really going to be able to handle it. So there's different ways of managing that. Some folks start developing, like an Access database or something even more robust than that. This graphic here is from a company called Aquatic Informatics, and their entire business model is focused around water flow and water quality data, and I think they're the ones that act like they're hired by the Geological Survey to manage their databases. Let's see. I'm not gonna go over this one because I have some other graphics that I think are going to be better. I did want to show you guys this graphic. I think this is a helpful one that will hopefully stick in your brain. As we take samples across a storm event, the concentrations are going to vary, right? So the initial sort of load or the initial concentration of whatever you're looking at is typically going to be much higher at the beginning of the storm event than at the end, after a lot of it has already been washed off. So they typically call this the first flush, and I think these are both pretty nice graphics that show that. You can see how at the very beginning we've got this really turbid water, and as you go through the event, it sort of clears out. And this is that graphic is from this sample tray right here. Kind of an important thing to know in terms of characterizing urban watersheds. The other thing to know is that in general, if you're taking a bunch of samples of pollutants, just any of them in an urban watershed, they're typically going to fit a log normal distribution. So you'll have a lot of, let's see, maybe this will help. If you think about sampling over this storm event and then way out, like if you keep going out, you're going to have a lot more samples that look like this than look like this, right? Because you have a lot of time in between the next storm event. But then you have that storm event again here, and you'll have this kind of samples again. So you're going to have a lot of samples that have lower concentrations, but then a few samples that have really high concentrations, so that's not going to be a normally distributed data set. Okay, just something that's important to know. Also wanted to just show you guys this graphic really quick. This is a really important tool for those of you guys that are doing like land use impacts on water quality. The National Stormwater Quality Database, back in I guess it was like the late 90s, they took like a zillion samples at outfalls across the US, and they tried to look at how median concentrations of various pollutants vary across different land uses. So these box and whisker plots are showing total suspended solids and total phosphorus for various land use categories. Okay, so if you have a question about typical concentrations for various land uses, like you're trying to do some sort of a GIS analysis, the National Stormwater Quality Database is a really, really good resource. They have all this information published, and that you can actually get the database if you want it and do your own analysis. So they've since updated it based on more data since the 2000s. But kind of an interesting spread here. Solids here, for example, it looks like freeway land use has the highest concentrations, and this is in a log scale here, so it's stretched a little bit. Remember that this is concentrations too. This isn't loads, so loads would look a little bit different than that. I've got some resources for you guys if you need information like that. The NSQD is linked up here, along with a couple of other places that have useful water quality data for your own research. And then I have the references to the presentation are at the end. That's I think all I'm going to do today. Does anybody have any questions or comments about the lecture for today? Okay, everybody good? Okay, so today I will distribute your documents to your peer groups. I probably am just gonna, I'll maybe just email them or something like that. I'll figure out the best way to do that. Oh, I can do that. Yeah, you showed me how to do that. Okay. Well, I'll see if I can figure out how to make that work. That would probably be easier. So, okay, cool. Thank you, Megan.